10.2. They both deal with hypothesis tests. We just finished 10.1, which was an introduction to hypothesis tests and how to set up the hypothesis test. But I believe it's really important we do 10.3 first because that's with the means, and we just covered the means. So I think it's good to flow with that. Go right off, we just had to pull out a t-table and look at some t-scores, so we'll just stay with these means. These problems deal with some population mean, and I think it'll flow better. And then we'll cover 10.2. 10.2 is a hypothesis test for a population proportion. Okay? So we'll do 10.3 first. I think you'll like this. You'll notice it's not like this stuff. This stuff's kind of fun. This is the coolest part of the course. Because someone's making an educated guess. Someone out there is researchers. And we're going to see if the results are basically statistically significant. All that probability stuff we did. Like all that stuff we did with probability, now we get to apply it. Everything's based on chance. So we're looking at like, well maybe, I think this is what's going on in this world, or researcher believes that. Well, it's all based on chance. And do you remember what we considered basically rare in this course?
Less than 5.
Less than like 5%. Now it's not always the standard. We know that. Some things it might be less than 1%. You know, some you consider something less than 1%. They will give you that number in the book though. I'll talk about that. So, but when we get results where we're getting like, you know, a 1 in 1,000 chance, that's when we're going to challenge it. That's when we're going to have the evidence to go against it. Because we're going to say, boy, that's a very, very, very unlikely, you know, occurrence there that something happened. So that's what's going to provide us with the evidence. So this whole thing, it's kind of cool. Everything is based on probability, right? Everything's based on probability. And we all know when there's like a 25% chance of something happening, it could happen, right? That means like every 4 times it could happen. 25% chance. But when it's what? Really small, like 1 in a million, that's not happening, is it? Alright, so, hey, I'm going to start with the problem. The problem I'm going to do, it's like any problem in 10.3. I'm actually taking it from the previous edition of this textbook. Just because I figured everyone in this class would relate to it. I wanted to pick a problem to start with that everyone could relate with. We can all relate to the body temperature, right? Alright, so this was done in 1992, if you want to put down the year, and it was 3 scientists, and the first sentence is this. We're going to set up a hypothesis test and perform a hypothesis test. The first sentence is, the mean body temperatures of human beings is assumed to be 98.6 degrees Fahrenheit. So the first thing we're going to do is set up our hypothesis test, okay? So I'm going to get ready to start setting this hypothesis test up. So I can go here and I'll put, so this is the setup of the hypothesis test. This is the null hypothesis. This is the alternative hypothesis. I'll read that first statement again. The mean body temperatures of human beings is assumed to be 98.6 degrees Fahrenheit. They like to state the status quo in the first sentence. So, when I begin, which symbol do you think I'm using?
The left one.
Yeah, it's this one. Now you might go, well, if we're doing means, that's how I knew it. But did you hear a percentage? 98.6 degrees Fahrenheit. Now that's like a mean, so we're going to use mean. So I'll put mu, I'll put equals, 98.6. Good job, this is what we're doing. Hey, that'll be section 10.2. We'll do the row, which is the population proportion. Okay. Now what about this? This depends on what these researchers believe. It's their educated guess from all their experiences. The next sentence, it says the 3 researchers believe that the body temperature is less than that number. So what symbol will I put?
Less than.
So down here, when I'll use the same parameter, mu, the same number, 98.6, and then because they said less than, just like that. Cool? Any questions on this so far? And I do have to emphasize how important that is, because that symbol right there is actually going to dictate our entire performance of the hypothesis test. So we've got to make sure we get it right. But I know you can read the sentence. We know greater than means what? That way, less than means that way. So eventually you and I are going to be making a bell, drawing a bell, and we're going to shade one tail. So this is very important, that symbol. All right, now, here come some numbers. So every time a number, I think it's good to write it off to the side. So the first number is this. This is from his old text. All right, they recorded 700 measurements of body temperatures. And these were randomly selected humans. They did it for 3 days, if anybody wanted to know that, but we don't need the 3 days. So let's go down. They recorded, everyone, 700 body temperatures of humans over a 3-day period. So what is equal to the 700?
N.
All right, so I'm going to go up to the side on just to list this. We got, all right, well, you know, when you read these word problems, they're long. We just want to record the important stuff. So n equals 700. Hey, this is for means, isn't it?
Mhm.
So with means, everyone, we are going to use what's called a t-table. Remember with inferential statistics dealing with means, we always use the t-table. So I'm going to write this down right now. If n is 700, what would the degrees of freedom be?
699.
Yeah, we just subtract it by 1. And don't worry if you didn't know that. It takes a while sometimes. df is always equal to sample size minus 1. Degrees of freedom minus 1. All right, what's next? What else did they get from these 700 humans? The sample mean was 98.2 degrees Fahrenheit. They said the sample mean is 98.2 degrees Fahrenheit. Sample mean means x bar, right? Now, if you need to, write the word sample mean next to that, just so you know what that means. But I know everyone in here knows that's sample mean. All right, 98.2 degrees Fahrenheit. That's your sample mean. All right, standard deviation of the sample, 0.7. What's the symbol for standard deviation of the
S.
sample? S equals 0.7. Cool?
Can you use S of X bar in the way in the calculator they do it?
Yeah, that's a good point. All right, everyone. Just to let everyone know, the calculator puts a subscript X right there off that S. So just so you know that, the TID 384 does put an X on a subscript on that. Textbook just puts a what? An S when they're talking about the sample standard deviation. Well, feel free to put a subscript of X there. Okay. Everyone so far so good? There is a new number coming. We haven't talked about this yet, but I'll make sure to explain it to you. It gives something called the level of significance. And for this particular problem, everyone, they said the level of significance is 0.01. Now I'm going to change colors of chalk. So I did everything in white chalk so far, right? And if you want to be like me, you got a pen and a pencil, feel free to do the same thing. You don't have to do it today, but every time I do a hypothesis test, I'll do this. For the level of significance, I'm going to change colors and just write this number down. The level of significance, we'll explain what it means, is 0.01. Now look at the Greek letter they used for the level of significance. They used the Greek letter alpha. So we haven't seen that Greek letter yet. They like to use alpha. That's alpha, the Greek letter alpha for the level of significance. But I like to change chalk and keep it separate from all these numbers, which I did in the white chalk. You'll see why. When I draw our picture, we make our bell curve, I think it's important. Just to distinguish the difference between this and this. All right. So everyone, the first thing was, we set up the hypothesis tests. I'm just going to put a line here. You can check this off. The setup of the hypothesis test is complete. You go, all right, well, what do you do next? Well, someone did a study, they've got their results here. Before we go and perform the hypothesis test, we do have to verify our requirements. So let's put that down. We're going to verify any requirements to ensure that the distribution of the sample mean is approximately normal. Cool? That's what we're going to do. Verify requirements to ensure that the distribution of sample mean is approximately normal. What is it for means? Do you remember?
N greater than 30.
N greater than equal to 30. Everyone, is the sample size greater than equal to 30?
Yes.
Well over 30, right everyone? And we're fine. We're fine. Hey, also, do you remember I said it? They chose these people randomly? That's important. I'm going to write that down. A random sample. And when it was a random sample, so we have verified our requirements. All right, we are now going to perform the hypothesis test. All right. So we're going to start with what's called the classical approach. But right now, everyone, we are now going to perform the hypothesis test. And there's two approaches. We'll do both of them, because they both go hand in hand. One's called the classical approach. One's called the p-value approach. So we're going to perform the classical approach. With the classical approach, everyone, now that we know that the distribution of the sample mean is approximately normal, you and I are going to draw a bell. We're going to draw a bell curve. Now, before I forget, because I don't want us to get confused, am I using Z or am I going to use T?
T.
Because there's like a Z distribution and there's a T distribution. And with means, mean Mr. T, we always use what? So just as a reminder, I'll put a T in here. Just in the middle. Just let it stand out so I don't accidentally use Z with these problems. And then in the end, we can all discuss how troublesome it would have been if I accidentally did use Z. Because everyone, keep in mind, the T distribution was for very small sample sizes, right?
Mm-hmm.
That's a gigantic what? Sample size. I might as well whisper this to you. In this particular problem, it really wouldn't matter if we use Z, because that number's huge, isn't it? Isn't that close to 1,000?
Mm-hmm.
I mean, it really is. So if that sample size that big, it wouldn't make a big difference if we accidentally use Z. But it's good to stay what? Always consistent. Hey, we're doing inferential stats with means, we're going to use T. So we're going to use a T distribution. And what's T equal to in the middle? 0. What's T equal to like right there? 1. They're like z-scores. T equals 2. 3 standard deviations from the mean. What's T equal to here?
3.
T's negative on each side, right?
Mm-hmm.
If you want to label this. Sure. All right. So we're performing the classical approach. We've got our bell curve drawn. I am changing colors. All right, so when I have my yellow chalk out, I'm going to that level of significance. What I'm going to do is shade a portion of that bell curve. I'm only shading 1%, and I'm going to shade one of the tails. Guess which tail I'm going to shade? It's all based off that. Yes, very good. Gary, excellent. I'm shading the left tail. This is called a left tail test. Because of that symbol right there, this is telling me which tail to shade. I'm going to shade over here, but I'm only shading what? Not much. I'm only shading
1%.
yeah, 1%. So not much. If you want everyone, you can put an arrow, because this would shade what? Forever. Does that make sense? I mean, I'll move my verification of the requirements just out of the way so everyone can see this. That you're like, yeah, this bell curve, it really just goes on forever. And I'm saying the shaded region 1%, there's not much left over, but I'm going on forever that way. Shaded region. All right. You know when we did verify the requirements? Where n was greater than or equal to 30, and the sample was,
Random.
I'll write SRS for it, was a simple random sample. I'll keep that there. I just wanted you to see that this bell really keeps going forever, doesn't it? I shade 1%, but you can think of everything to the left shaded. All right. But when I put that in yellow chalk, this is the alpha level, which was equal to 1%, right?
Mm-hmm.
All right. There's two numbers we got to find in the classical approach. This isn't bad at all. We got to find something called a, well, it's not T. I mean, it's not Z, it's T. We got to find something called a T, crit. It's the critical T value. So off this wall of that shaded region, I'm just going to extend this line down here, and this marking right here, you and I have to find this critical T value. But feel free to just call it T sub crit. You know, but if you want to write it in words, you could say it's the critical T value. We have to find it. You go, well, how are we going to do that? Now everyone notice I'm with the yellow chalk. because we're gonna get the critical T value. And it's based off this number here. And it's based off the degrees of freedom. Alright? But that's what I mean. Sometimes students get confused, like, I don't know how to get the critical T value. That's why I like the color code. How am I going to find this critical T? I got my yellow chalk. It's based off this what? 0.01. So does everyone have their T tables? We're going to look at this T distribution. Look in the left column, excuse me, the top row for a 0.01. I want to see the 0.01 in the top row. So we go up to the top row, we're looking for 0.01. Then we're going to look over to DF, which is degrees of freedom. And we're going to line up the degrees of freedom, that's 700, with the 0.01 to come up with this critical T value. Now, is there a 700 in the left column?
No.
So we take the closest. What's the closest degrees of freedom you see to 700? Yeah, what's closer to 700, 100 or 1,000?
1,000.
We're going to use the 1,000. Cool? Gary, okay?
I thought the degrees of freedom was 699.
You're right. Oh, so the degrees of freedom, thank you, Gary, is 699. And I'm going to take the closest number to 699. Now there's 1,000 and 100. And Gary, thanks again. We're taking the closest number to this 699. So I'll write that down. We get 699 degrees of freedom. But the closest to this, everyone in that table, is the what? Is the 1,000. Well, it's fine. That's what we're going to use. So what do you all get when you line up 1,000 with 0.01? 2.33. What's after the 3?
0.
Now, everyone, look at my sketch. See, there's a reason. We just want to give you one nice table, right? There's something else I have to do. This isn't making sense. This is why I like to label these. T equals 0, T equals 1, T equals 2, T equals 3, -1, -2, -3. Doesn't a T-score on the left side have to be negative? So make sure when you're drawing your pictures and using